Hello everyone, welcome back. Today we are going to learn about data storage and the calculation of file size. So let's go ahead and take a look at the contents of this lesson. In this video lesson, we shall look into how data storage is measured, including the units of measurement for data storage, and we are also going to look at how to calculate the file size of an image file and a sound file. Before going to the nexus of today's subject, let us recall a few facts from our previous lesson. Any form of information needs to be converted into a binary format so that it can be processed by a computer. For a computer to capture sound waves, known as analog sound, it needs to store the sound in a digital format, that is, sequences of ones and zeros. Some characteristics of sound waves are amplitude, that we perceive as volume, frequency, that we perceive as pitch, and duration, that is, the length of time the sound lasts. Sampling is the first step in the process of converting a continuous analog signal to a sequence of digital numbers. While sampling a sound wave, the computer takes measurements of this sound wave at a regular interval called sampling interval. The sample rate, measured in hertz, is the number of samples in 1 second. When we magnify a bitmap image, we will see that it is made up of tiny elements called pixels. In order for the computer to store the image, each pixel is represented by a binary value. Image resolution refers to the clarity of an image as it appears on a screen or on paper. It is the total number of pixels in the image. The size of an image in pixels, that is the image resolution, is calculated by multiplying the width by the height of the image. Color depth or bit depth refers to the amount of color that each pixel can display. It is the number of bits per pixel on a computer monitor. A bit depth of 1 provides 2 to the power of 1, giving 2 colors per pixel. A bit depth of 3 will cater for 2 to the power of 3 colors per pixel. In its most basic form, data storage refers to the use of a recording medium to store data on computers or other devices. Everything on a computer is stored using signals which are either on or off. One such signal is called a binary digit or bit for short. The two possible values of a bit are typically written as 1 or 0, or true and false. On a computing chip, they are represented by high and low voltages. An individual bit cannot store very much, literally one single on or off, so there is a need to group them into larger amounts. Everything in computing is based upon combinations of bits. When bits are grouped, there are a variety of methods for interpreting them collectively. Each binary digit is termed a bit. The state is represented by a single binary value, usually a 0 or 1. 4 bits, or half of 1 byte, is known as a nibble. A byte is the name given to a group of 8 bits. It is the unit most computers use to represent a character, such as a letter, number, or typographic symbol. All memory storage is expressed in terms of bytes, but we need to consider even larger amounts of storage due to the rapid evolution of technology. All greater units are typically referred to by their shortened names. This means that we could keep on adding more prefixes to talk about more and more data. The prefixes for the multiples of quantities such as file size and disk capacity are based on the decimal system as defined by the International System of Units. For example, the prefix kilo means 1000 times the given unit, so that the kilometer is 1000 meters, and so on. Humans and computers use different numbering schemes. People use base 10, where each digit is worth 10 times the digit before it. On the other hand, digital computers use binary, which works with powers of 2. Most storage manufacturers measure and label capacity in base 10, but have you ever wondered why your hard drive, which nominally has a storage capacity of 500 gigabytes, only has actually about 488 gigabytes? This is because digital computers are fundamentally binary systems, and as such, their low-level behavior is described in terms of the binary number system based on 2 digits, the famous zeros and ones. For data storage, what was thought of as a kilobyte is in fact a kibibyte, and it is equivalent to 1024 bytes, not 1000 bytes as might be expected. To understand how these units all fit together, it is helpful to look at data units from smallest to largest. This diagram shows the relationship between the data storage units, and it gives an idea on the suitability of the units for data of different sizes. In a data storage size of 1 byte, we have 8 bits. There are 1024 bytes in 1 kibibyte. 1 mebibyte is composed of 1024 kibibytes. Similarly, 1 gigabyte contains 1024 mebibytes. Above tebibytes, we have pebibyte, exbibyte, etc. Now, let's learn how we will calculate file size required to hold a bitmap image and a sound sample. In order to calculate the size of an image file, we need to take into account certain values to use in our formula, namely, the number of horizontal pixels, the number of vertical pixels, and the bit depth of the image, that is the number of bits per pixel. So, we first need to establish how many horizontal pixels there are. We multiply it by the number of vertical pixels to get the resolution. If the color depth or bit depth is 8 bits, the file size will be 48 multiplied by 8, giving 384 bits. Let's try a few examples. Calculate the size of an image with a color depth of 4 bits, height of 12 pixels, and width of 20 pixels. Give your answer in kibibytes. How do we unpick this? We know that the formula for image file size is given by resolution multiplied by color depth. Resolution is height multiplied by width. Replacing with the correct values, we obtain 12 times 20 times 4. We will end up with an answer in bits, but we want the answer in kibibytes. How do we convert bits to kibibytes? Well, we divide by 8 first to get the answer in bytes. For the final answer in kibibytes, we will further divide by 1024. Example 2. The following monochrome image has a resolution of 800 times 600 pixels. Calculate the image file size in kibibytes. Being that it is a monochrome image, there are only 2 tones of color available, black and white. The number 2 in binary is 2 to the power of 1. This gives the image a bit depth of 1. Proceeding with our calculation, we have got 800 times 600 times 1 divided by 8 times 1024. That gives us 58.6 kibibytes. Let's look at another question with the same image, but this time having 16 bits of color. Now, 16 is equivalent to 2 to the power of 4. This gives the image a bit depth of 4. Proceeding with our calculation, we have got 800 times 600 times 4 divided by 8 times 1024. That equals 234 kibibytes. Try out this question. Note that 1 megabyte is equal to 1024 times 1024 bytes. Next question. A photograph is 1024 times 1080 pixels and uses a color depth of 32 bits. How many photographs of this size would fit onto a memory stick of 64 gigabytes? The answer is 15,534. Are you up for a challenge? Solve this last question on image file size. To calculate an audio file size, there are 3 features that we need to know about. They are the sampling rate, that is how many times the sample is taken in the actual file, the bit resolution, which is equivalent to the bit depth of an image file, but this time, instead of colors, it is sound. It is how many types of sound are available for the audio track. The final value required is time, which means how long the sound will go on. In order to find out the size of a mono sound where the sound is being sent down one channel, it is basically the sound rate times the sample size or resolution times the duration. The difference with stereo is that sound is split and sent down into 2 channels, so it is the same actual formula times 2. So, let's give it a go with an actual sound file. To work out the size of the sound file, we need to do the sample rate times the resolution times the duration. We start with the sample rate, which is the number of times the sound is being sampled per second. On the x-axis, we have 3 seconds, and each given second, the sound is being sampled 6 times. This is given by the vertical gray lines. So, the sample rate is 6, meaning that 6 samples are being taken per second. We multiply it by the resolution. This is the sample depth, sometimes known as the amplitude. This is the number of bits which are being captured at every single sample. We can see here there are 16 various graduations on the left-hand side which the sound can be captured at, and those 16 variations can be captured in 4 bits from 000 to 1111. So, we have a resolution of 4 bits. Finally, we multiply it by the duration of the sample in seconds. We can see that the file is 3 seconds long. So, we end up with 6 times 4 times 3, which is 72 bits, and if we divide that by 8 to get bytes, this sound file is 9 bytes in size. Let's look at an example. Calculate the size of a 5-second sound sample with a bit depth of 16 bits and a sample rate of 8000 Hz. Give your answer in kibibytes. So, let us recall that the size of an audio file is given by the product of the sample rate, the sample resolution, and the length of the sample. We can gather from the information provided that the sample rate is 8000 Hz, the sample resolution, that is bit depth, is 16 bits, and the length of the sample is 5 seconds. File size will hence be obtained by calculating 8000 times 16 times 5. So, we are dealing with a file size of 64,000 bits. How many bytes does that make? We divide 64,000 by 8. To obtain the answer in kilobytes, we divide again by 1024. That makes 0.78 kilobytes. Here, we are asked to calculate the size of the file given a sampling rate of 44.1 kHz, a sample size of 16-bit, and a length of 60 seconds. We have also been told that the output is stereo. Let's note down the important details. The sample rate is 44.1 kHz, that is 44,100 Hz. The sample resolution is 16 bits, and the length of the sample is 60 seconds. Let's not forget the type of audio that we are working with. It is a stereo sound, and hence we have two channels to consider. File size will therefore be obtained by calculating 44,100 times 16 times 60 times 2. That gives us 84,672,000 bits, which we then divide by 8 to convert into bytes. If we want to convert into megabytes, we divide by 1024 to the power of 2. That makes 10.09 megabytes. Test your understanding with this question. Calculate the file size of a mono sound having the following properties: duration 30 seconds, sample rate 44,100 Hz, and sample resolution of 8 bits. The answer is 1.3 megabytes. Ready for a last challenge? "19 extra sound files can be added to the CD. Let's review what was learned today. Computers work in binary digits combining zeros and ones in countless patterns. All memory storage is expressed in terms of bytes. When 8 bits are combined, we get a byte. Bytes are used to store a single character, whether it is a letter, number, or punctuation. Data storage is usually defined using metric prefixes, but computers use binary, that is base 2 mathematics, instead of a decimal system. Since we use binary to represent the data in a computer system, it has been decided to group the bytes into 1024 bytes. Sound file size is obtained by calculating the product of the sample rate, the duration of the sound file, and the sample resolution. The size of an image file can be worked out by multiplying the color depth with the image resolution, which is given by the product of the image height and the image width. Thanks for watching. Stay tuned for more video tutorials. Goodbye.